about anything.
Yeah, okay. So I will start with the basics and see whether I have time to do anything advanced.
Yes.
Yeah, so I'll write on the whiteboard and I will put off my video because this camera is inverted now.
Okay.
Okay, so you can ask any question at any time. Don't wait for the end because yeah, you may have questions, even basic questions in the beginning. So feel free to ask. So the topic is just a minute. Yeah. Yeah. So I will discuss the basics of lattice theory and maybe see some applications to polynomial factoring and a famous public key crypto system called NTRU. Okay, so this NTRU is famous because it's a good substitute to the RSA public key crypto system. Okay, and even if there are quantum computers built, and even if you can solve integer factoring problem, this true crypto system may still survive, may still be secure. So this is this is an interesting feature of this crypto system. So we'll see why. So what is a lattice? So a lattice is like a grid. Just hold on. Something crashed. Yeah, maybe I have to reboot this. Just bear with me.
Yes, sir.
Yeah, sorry, I had to reboot. This whiteboard is sometimes problematic. Let me try Zoom whiteboard. Is this visible and am I audible?
Yes, sir.
Okay. Yeah, the last time the screen just froze. Let's see whether it works here. Okay, so yeah, so I was saying that lattice is like a grid. Okay, so for example, you can have this as the XY axis. And then maybe you pick this vector. Okay, you pick these two vectors starting from the origin, these dotted vectors. And then you keep placing this after translation, like this. Okay, so these points that you get, this point, this point, this point. So these red points, if you can see the color, okay, so this you will get everywhere to infinity. And the set of these red points is called a grid. Okay, so that is the picture. And then obviously picture will not be enough to do computations. So we will need a proper definition. So what we are doing is we are actually taking Z linear combinations of given vectors. In the picture, there were two vectors, but in general, there might be M vectors. In the space R to the N. In the picture, N was equal to 2. So in the Euclidean n-dimensional space, this set of Z linear combinations, okay, this defines a lattice. We write it as the lattice generated by vectors B1 to Bm, which is, again, the definition is formally it has these elements. So take arbitrary integers and then multiply gamma I with bi and then add it up. Okay, so that is how you get these red points in the picture. So I added I multiplied by 1, b1, if you think of this as b1. This as b1 and this vector as b2. Then the first point is 0 point, then you have b1, then you have 2b1. And similarly, in the other axis, you have 0, b2, and then 2b2. And everything else are actually combinations. Okay, and then 2b1 plus b2 is this point, and so on. So you can do this also in the negative direction. So you will have a point here also. So you have a point here, you have a point here, and so on. Excuse me. So yeah, so you can do it in the positive negative x-axis and also positive negative y-axis. So you can fill the whole space. But you can see that this is a very coarse subset of the plane. Okay, this doesn't contain the whole plane. This is coarser than. So it's a density 0 object in the space, but it's a very useful thing because somehow these integral linear combinations is what we use in computer science. Okay, we don't use real combinations in many situations. We just want integral linear combination. Another way to write this is you can write it as ZB1 plus ZB2 ZBM. Okay, but I'll not use this notation. This is the same set. So in the example above, the lattice is generated by 1 0 vector and the 1 1 vector. Right, this is how I define. So this is 1 here in the x direction, and this point is 1 comma 1. So in terms of vectors, the first b1 is 1 0 and b2 is 1 1. But then you can see that this is also equal to the lattice generated by 1 0 and 0 1. If you had started with something else, like for example, if you started with this and this, the orthogonal axis, still you will get the same lattice. You will get the same red points, right? So the basis is not unique. There are many ways to get the same lattice from different bases. And if you instead take zero one, this is a coarser lattice. So coarser meaning that it will have fewer points. Yeah, because for example, 1 0 is not there. Okay, so you will get actually fewer red points, but it will be a subset of the red points in the picture. And other important thing is a term which we use is that what is the shortest vector in L in the above? So the shortest vector here in L is, can you guess? Amongst these red points, each red point is seen as a vector, right? Starting from the origin. So what is the smallest distance that you have? Anybody from the audience? The smallest distance from the origin is B1
Sir,
itself. Yes,
B1.
B1 itself, right? And we know that 0, 1 is also there, so 0, 1 as well. Anyway, so so yeah, this is the lattice picture, and you have seen the shortest vector. There are actually 4 shortest vectors here in all the 4 directions. And all other points are either it is 0 or they are further away. So our goal in this whole talk, the central goal, is actually to get this vector. Okay, that is the central goal, and this may not be clear immediately, but many practical applications actually need this this algorithm, or they want to solve this problem, the problem of getting closer to the origin and formally computing the shortest vector length in the lattice. Here it was particularly easy because one of the basis vectors itself was a shortest vector, but this may not be the case always. And then after some, let's say, computing B1 minus B2, the length decreases. Okay, so you have to actually compute the linear combination, which gives you shortest vector. So that is the computational question. The computational question of SVP, shortest vector problem, is find vector V in your lattice which we are denoting by L, such that the length of the vector is the minimum amongst all the vectors in the lattice. So U should not be 0. And yeah, let me not use this bar. So 0 is, U is not 0 and it is in the lattice. Okay, the minimum vector, minimum length vector, non-zero in the lattice, which we can also write in short as minimum of L minus 0. Okay, it's the shortest vector in the lattice, which is non-zero. Now this V may not be unique, which is why we are only talking about its length. You can so V is not unique, as you saw in the previous example, but the length is. Do you see that the length is unique? Has to be unique. You can take this as an exercise. Inform me. Are the slides visible and audible?
Yes, sir.
Okay. Any questions about these two definitions? The basic notation. you can ask whenever you want. So what is known about this question? It is known that so it's a theorem. It's not a conjecture. It's a theorem that was shown by ISTE-AICTE, that shortest vector problem is NP-hard. Okay, so although it seems to be a easy to visualize geometric problem, in the general setting, as n increases, as m also increases, shortest vector problem becomes NP-hard. So if you solve this problem efficiently, then you will practical problems which are NP-hard. And second thing which was shown, which is even more surprising, this was shown by Michanchio around the same year, is that constant approximation of SVP is also NP-hard. What is constant approximation? So constant approximation means that don't find the exact length V. Just find a vector which is, let's say, 2 times the shortest length. Okay, or 100 times the shortest length. So this constant means find V in the lattice such that the length of V is less than equal to some constant times the minimum length. Now C is an absolute constant, like 100. Okay, so find a vector which is at most 100 times the minimum length. And so then what questions remain? If it is NP-hard, then there is no point solving this or trying to solve this, unless you believe NP is equal to P, which very few people do. So we have to look at other questions. So one next question that you can look at is there a polynomial in n approximation? To SVP. Okay. For example, n approximation. It will mean that instead of C, you put n. Find a vector which is at most n times the minimum, the shortest vector, the shortest length in the lattice. Even this is an open question. We don't know a solution to this. So we can relax it and we can ask for a 2 raised to n approximation. To SVP. Okay, so which means that you have to find a vector V in the lattice which is less than or equal to 2 raised to n times the minimum in the lattice. So remember, M is like vectors defining the lattice. And in that exponential, this is exponential approximation. In the input size. So what good is that, right? Is this a non-trivial question? And if it is there an algorithm for this? So the point of this lecture is to show that this can be solved in a polynomial time. In fact, in deterministic polynomial time, you can find an exponential approximation to SVP. Is the question clear? Or do you have other questions? Then you can ask. Okay. So there is an amazing algorithm for this. For question 2, and which is called the L-cube algorithm. What is this L-cube algo? This L-cube stands for Lenstra-Lovács. They wrote a paper in 1982 where they solved this problem. So I'll discuss the L-cube algorithm now. So actually the L-cube algorithm, it finds an L-cube reduced basis. Given by generating vectors. And we can assume that these vectors are integral. Okay, potentially they could have been real vectors, so real coordinates. But since we are in computer science, we can assume the coordinates to be actually integers. Okay, not even rationals. Okay. So let's see some of the ideas of this. We don't have enough time, so we will just look at the main ideas, and I leave things for you to prove as exercise. Okay, so so can we assume this B1 to Bm as linearly independent? Right, these vectors, integral vectors that you are given, what do you do if they are dependent? Now note that lattice is not a vector space. So when they are dependent, we cannot just, if Bm is dependent on the previous ones, we cannot just delete Bm, right? Because maybe in integral combinations, it is helping. So this becomes a non-trivial issue. I claim that I claim that we can get to this. Suppose the vectors that you are given, two vectors, these are B1 is B11, Bn1 coordinates, and B2 is B21, B B1n and B2n coordinates. Okay, the first column is B1. This is B1, and this is the B2. And suppose these are linearly dependent over R. So what do you do? So I'll show you a general process. The general process is you compute the GCD of two numbers. You focus on the first row. This is the D. By Euclid's algorithm. Does everybody know what is Euclid's GCD algorithm? Or what is GCD? If you don't, you can ask. So compute the GCD, and then using the GCD, what you can do, actually GCD by Euclid algorithm is a combination of these two numbers. Okay, it will give you A1 and A2 integers such that the linear combination is G. So it will be given to you in a way that you can to the following form. B times another matrix, which will look like G and 0 in the first row, and then remaining things. Okay, so the first row has basically transformed. The first row I have transformed from B11, B21 to its GCD, and then second is 0. Once I get GCD, I know that B21 is divisible by G. So I can take an integral linear combination, subtract the first column from the second column. Okay, so what will happen is if the two columns were linearly dependent, then now will just become 0. Okay, so this process is called Gauss-Euclid trick. Let me do it on the second page. So from B, you get a matrix B prime. Where this U from the Euclid algorithm will be a matrix whose determinant is plus minus 1. Okay, this matrix is also called unimodular matrix. So determinant being plus minus 1 means that okay, that's all I want from you. This is what Euclid's algorithm ensures, that the U matrix, actually its inverse also exists. So since its inverse also exists in integers, the lattice of B and the lattice of B prime, they are the same. Okay, so that is exercise 1 for you. So show that the lattice of B is the lattice of B prime. So when we move from basis B to basis B prime, the lattice doesn't change. And if B1, B2 are linearly dependent, then this second vector that we got, okay, here we got a vector B1 prime, B2 prime. B2 prime will be 0. And so we can drop it. Okay, which will immediately, if you prove this, then you will immediately see that we can assume, or we can convert can reduce to basis B1 to Bm, which is R linearly independent. Okay, so this algorithmically answers the question, can we assume our lattice to have linearly independent basis vectors? So the answer is yes. You can actually, given anything, you can convert the basis to actually independent vectors, and they will still be in the lattice. They will still generate the same lattice. Okay, so this exercise 1 will so this means that M in particular will always be less than or equal to N. Okay, you cannot have more than N basis vectors of a lattice. So since we have a basis now, which is independent basis now of a lattice, we can actually do some things that are done in linear algebra. Okay, so that brings us to orthogonal basis. We can find an orthogonal basis. Of this B1 to Bm that is given to us. Now, let me remind you how this is done. You must have seen this in linear algebra courses. So again, you have vectors B1, B2 in some general position. And if you look at the vector space generated by them, not the lattice. Okay, so then the projection of B2 on B1 is this. And what is this vector? So this is basically B2 in the direction of B1. Right, so in the direction of B1, which is given by B1 divided by its length, that's the unit vector. So for that unit vector, you compute the inner product that gives you the length of the projection. And B1 by B1 norm gives you the direction. So that's the that's the vector when you project. So if you remove this projection from B2, then you will get orthogonal component. And this orthogonal component is called B2 star. Okay, so let me use this opportunity to introduce a notation. So this is B2 comma B1 by B1 norm square times B1. And I can write it, I can define mu21 here. So mu21 is a real number. Okay, it's a real number because division is happening. So it may not be integral. It's not integral. And B1 is your integral vector. So that's it. That is what the projection of B2 on B1 is. And this orthogonal component B2 star is then given by B2 minus mu21 B1. Okay, so the orthogonal basis of this vector space is B1 comma B2 star. This is the definition of B1 B2 star is the orthogonal basis. Why orthogonal? Because if you compute B1 comma B2 star inner product, it's 0. Okay, you can check this. So I can call this B1 also B1 star. And then B1 star, B2 star is the orthogonal basis. Okay, so this is how I will convert to an orthogonal basis. So the problem is that this mu21 is not integral, generally speaking. And so this B2 star may not be in the lattice. Okay, so you cannot find orthogonal basis in the lattice. So the first example I gave you on slide 1. Okay, here actually we were able to find an orthogonal basis B1 star, B2 star. And so B1 became the shortest vector. So it was a very nice situation. In general, that will not happen. A shortest vector is harder, becomes harder. Yeah, did I give you exercise 1? Okay. I should have called this exercise 1. Okay, show that determinant of u is plus minus 1. That exercise 1. Exercise 2 was the lattice remains unchanged under this Gauss-Euclid trick. And exercise 3 for you is now to show that if this B2 star happens to be in the lattice, then the minimum of B1 star, B2 star happens to be the shortest vector. Okay, so orthogonal basis will immediately give you a shortest vector if orthogonal basis is in the lattice. Okay. Any questions till now? So in general, as n increases, this is orthogonalization. Process. Okay, so the equations that you get is B1 star is B1, B2 star is B2 minus mu21 B1, B3 star is B3 minus. So remove the projection on B2. So that's mu32 B2. So on. Ultimately, BM star will be BM minus M1 B1 and M minus 1 B M minus 1. Okay, so these are the orthogonal vectors forming the same vector space. But the problem always is that this may not be in the lattice. So this is a more refined, this goes outside the lattice basically. Yes, but if it is going outside the lattice, how will this help compute the shortest vector, right? Why are we doing this? So any suggestions from the audience? How can you use this to get some information inside the lattice? Any suggestions from the audience if you have seen this before?
Sir, we can take nearest integer to this mu values.
values in general may be any real number. It may be smaller than 1 or it may be bigger than 1. Right? So if it is, for example, 1.4, so you can round off 1.4 to 1. And if it is 1.5, then you can round it off to 2. Okay, so you can actually round it off and and then you can, since it becomes integral, mu becomes integral, mu ij becomes integral, you can then stay within the lattice. Okay, that is the point. So let us explore that idea. So L-cube algo approximates this. By this I mean GSO. By taking for mu ij takes, it rounds off mu ij. To integral. Okay, so basically 1.4 becomes 1.4 becomes 2 and so on. Okay, that's the idea. So the mistake that it is making is less than equal to 0.5. Right? That's the mistake that you make. So what is the meaning of that mistake in the real geometry? So that basic idea is the mutual angles greater than equal to 60 degrees. Okay, instead of exactly 90. So orthogonalization meant that BI BJ angle has to be 90 degrees. Instead, we are relaxing it to 60. What is the connection between rounding off and this angle? But roughly, this is what is happening in the real geometry. And the advantage is that we remain in L. Okay, if we make it 90 degrees, more than 60 degrees, then we can manage it in the lattice. And now all that remains is to analyze these points in the lattice that we have obtained. And so now we come to the reduced basis concept. I don't think I will have time to analyze it, but let us. So L-cube algo will basically find L-cube reduced basis of the given lattice denoted by vectors C1 to Cm such that so two main conditions. First condition is that for all I greater than equal to j, if you do the Gram-Schmidt process, GSO, then the mu ij is a small fraction, smaller than half. Okay, as I said that the remaining mu ij part is only most 0.5. And geometrically, you can interpret this, see, because mu ij is kind of inner product. Inner product has cos theta. So if cos theta is less than equal to half, then theta is more than 60 degrees. Okay, so this is the calculation with the real geometric motivation of 60-degree angle. Yeah, and second thing is really a byproduct of this L-cube analysis. What it will say is that these CIs, they are not growing very fast. Okay, they are somehow related. And that relation is given by this. So this is saying, I mean, the best way to understand this is to take n equal to 2. So what this is saying is in the left-hand side, you have Ci star. So this is C. It's basically C2 star plus mu21 C1 star, which you can see is also equal to C2. So this is saying that C2 is actually comparable to C1 star. It's not smaller. I mean, it actually it's not much smaller. This is what it is saying. So it says that Ci plus 1 not too small compared to Ci star. Okay, that's what it is saying. It's saying that in some sense, these CIs are sorted. Okay, I mean, this is false, but somehow it is trying to achieve that. Note that root 3 by 2 is around, what is it, 0.85, right? So it's less than 1. So Ci plus 1 may be smaller than Ci star, but not much smaller. So these two properties actually give you an approximation to lattice vectors, especially the shortest lattice vector. And the way this algorithm works, in fact, let me give you some exercises. So do this exercise 4. So Ci star times 1 by root 2 is less than equal to Ci plus 1 star. Prove this fact. Okay, this again is saying that Ci plus 1 star is not much smaller than Ci star. And just from the definition of reduced basis, which I have written, just from this, you can deduce SVP. So you can deduce that the minimum vector in the lattice is at most C1 star and is at least C1 star times 1 by root 2 to the m minus 1. Okay, this exercise 5 actually follows from exercise 4. And exercise 4 follows from the definition. So these are very easy to prove. And what this tells you is that C that's what you learn. C1 star, which happens to be C1, is an SVP approximation. It's an approximation, this root 2 to the m minus 1, which is like root 2 to the n. Okay, it's a 2 raised to n minus 1 by 2 approximation. To SVP. Is this clear? I'm afraid we cannot do more than this. This is all the time we have. So if you have any questions or if you solve the questions, exercises, you will understand more. And L-cube algorithm, all it does is that it uses this GSO approximation. It rounds off mu ij. And then it checks whether this condition 2 is satisfied. If condition 2 is not being satisfied, then it swaps Ci and Ci plus 1. Okay, remember, because this is like, it is trying sorting. It is trying to sort Ci's. So if the correct order is not there, it swaps them and then repeats. Okay, so it's like a sorting algorithm, a slow sorting algorithm.
Sir, how we will show that these Ci star will satisfy this condition too?
Condition 2.
Yes, sir.
Right. So if these one and repeat, that's the L-cube algorithm. Is that clear?
Okay, sir. Okay, thank you.
GSO with rounding if condition 2 is fails, then you swap and then you repeat, go to 1. Okay, so keep doing this. Do rounding GSO. If it fails, then swap the CI plus 1. So now your set has changed. Again, do GSO. And GSO is very sensitive to the set, right? You can see that GSO algorithm, the way we have defined it here. If you change the order of BIs, if you flip B1 with B2, swap B1 with B2, then the answers change. So things can drastically change, and you keep doing this. And of course, the question is, why will it ever stop? Or when will it ever stop, even if it stops? And that I cannot analyze here. That is a long analysis. It uses volume of the lattice. So using volume of the lattice, you can show in exercise 6, you can show that it will stop in time n to the 6. Okay, by using volume. You have to develop this analysis and show that not only it stops in finite time, it actually stops in time n to the 6. Is this clear?
Sir, is there any condition in which this algorithm will fail to give an output?
No, this exercise 6, if you do, this finishes L-cube description. It always succeeds, and it always gives you C1, which is a 2 raised to n by 2 approximation. Is that clear?
Okay, sir. Thank you.
Okay, so this is a giant algorithm. It holds extreme importance in several areas of computer science. So in case you haven't heard, applications of L-cube. It is used in factoring integral polynomials. Okay, it is used in general in computational algebraic number theory. It's used to hack crypto systems like knapsack problem or hacking lattice crypto systems. Or to find Diophantine approximations. And many other things, in fact, even in some cases, integer factoring. Okay, so there to read about them. So read one of these. Look at the analysis. Okay, so now I have just 5 or 10 minutes, right? Maybe the organizers can confirm.
Yes, sir, you have. Yes, sir.
Okay, so let me just complete N-true. What is N-true? Maybe that is more interesting for you. The N-true public key crypto system it's a public key crypto system. So, for example, when you interact with your bank, the bank can use it. Okay, because so bank will publish its public key and will not publish its private key. So you only have bank customer of the bank. You only have this public key which you can use to encrypt your password, internet password, and send this to the bank. Okay, and then bank can confirm that you are the customer with that bank account. So it's one of the most useful crypto system primitives, this public key. And true in particular stands for nth degree truncated polynomial ring. Okay, so NT, R, and U as a vowel. And true is this. And what is the ring? The ring is so R is the ring ZX mod X to the N minus 1. Okay, this is why it's the nth degree truncated. So these are polynomials N minus 1 degree. Okay, so each polynomial has N coefficients and degree is N minus 1. And when you multiply two polynomials, you will get degree more than N minus 1. But then you convert X to the N to 1. Right? So the arithmetic here, if you are not aware, the arithmetic is you will convert X to the N to 1, X to the N plus 1 to X. N plus N minus 1 to N minus 1, X to the 2N to 1, and so on. Okay, so you don't need degrees more than N minus 1. It loops around. That's the truncation. So this was proposed by Hofstein, Pfeiffer, and Silverman. In Crypto Conference 96. And why are we calling it a lattice crypto system? Well, R is a lattice. Right, with basis one X to the N minus 1. So if you think of 1x, x square, xn minus 1 vectors, then you are taking linear. So it can be seen as a lattice. And but this is more than a lattice, right? It's also an algebra. So not only you are doing addition, but you're also doing multiplication. So it's a very rich object. And the security of the crypto system is based on this hardness assumption that L cube algorithm can't approximate SPP fast enough for dimension 2n if n is 512. Okay, in other words, if the dimension is more than 1000, then the algorithm takes something like 1000 to the 6. So it's very slow. And the approximation it gives is 2 raised to n, which is also a bad approximation. 2 raised to 512, right? So that's the hardness assumption, that L cube is not fast enough. And the advantage smaller keys, public and private keys are smaller. So RSA these days requires more than 2000 bits. And here you are able to do 1/3 or half of that. So yeah, I think the time is up. Let me just quickly give you the steps. This is 251, sorry. No, 2n, I'm making a mistake. N is 512. No, actually, yeah, it has to be smaller. That's why small keys. Yeah, 2n is just 500 actually. So it's that small. But still the time needed over this will be quite a lot for L cube. That's the hardness we assume. So everybody knows NPQ, and everybody knows these support bounds. Something called DFDG, DMDR. Think of it as around 80. is random polynomials fg from the ring f has df many plus ones and df minus 1 many minus ones. Right? In particular, if you compute f at 1, you get 1 because there is one extra plus. So f has only plus 1, minus 1, 0. It's a ternary polynomial. And g is similar. It has dg ones and dg minus ones. This is also ternary. Public key of the bank that you will use to encode is the polynomial h, which is gx by fx mod q. Right? Q is 2 raised to 7. So h has these coefficients up to 0 to 127. And finally, we come to encryption decryption. So you are the client or the bank customer, and you have a message M, a password. You want to send this to the bank. So what do? Your ciphertext E will be this polynomial M that you have. M is again, it has dm plus ones and dm minus ones. You can assume all that. Okay, these are all ternary polynomials. Okay, so you have this password M, you add PRH. P is in fact 3. R is a random polynomial that you choose on client side. H is the public key. So you send this to the bank, right? So nobody else knows R. And everybody knows P and H. Now the question is, can somebody not answer that question? Let me just say what the bank will do. What the bank will do is bank has gotten an E. It wants to decrypt it. So it will do in 3 steps. It will multiply it with its secret F or Q. Compute it mod P. Now the effect of this should be that this PRH should get deleted. Okay, that's the intuition. It should get deleted and you should have FM. And so it multiplies it with F inverse. Okay, this comes out to be M. That's the decryption. That is what you wanted to send. Also, and your final exercise is analyze its security. completes my talk.